Okay, Anthony, it's all yours.
Good evening, group.
I will stop sharing. And there you are.
Good evening, group. My name is Anthony Harder, and as you know, I have spent almost my entire career in distributed systems. My master's project was a 1200 system distributed server network in industry, and that was before there was any cloud stuff to assist us. That was there was nothing in the cloud. The cloud was kind of like vapor at that time, a wishful thought that computing has made progress on over time. Our speaker tonight is Professor Ali Anwar, and he is one of the most recent addition to the Department of Computer Science at the University of Minnesota. He arrived last spring, so he's a very recent addition to the department. And his interest is in the intersection of distributed systems and machine learning. And his topic for tonight, I'll give a very high overview, and he will go into detail on it, is in the topic of federated learning and how to use models to ensure privacy or improve privacy, and use them to train them on source data that may be secured or sensitive. Professor Anwar is, as I said, a professor at the assistant professor at the University of Minnesota, and he has patents and projects. You can read the introduction, his bio on the introduction, for some details on that. With that, I'm going to introduce Professor Anwar and let him give us a talk on distributed systems, machine learning, and federated learning. Professor, take the helm.
Thanks for introduction. I think I would need to have access to share my screen. So if you can share screen and click enable participants.
Sanjay?
So I enabled all participants to share screen. Ali should be able to do it now. I was hoping we would make you a co-host. Apparently, I don't have the control because I am just a co-host.
So I think someone is sharing screen. I can.
I'll stop. I got it. There we go.
And Dick, if you can make Ali your co-host. So
I think I can share my screen.
Okay, cool.
Yep. There we go.
Okay.
Yep.
Okay, so I can. Thanks for the introduction. So I can briefly tell you a little bit more about myself. So I did my PhD in 2018 from Virginia Tech. The area that I did in my PhD was completely distributed systems, without anything related to machine learning. But I gradually moved from distributed systems to ML while I was working for IBM Research. So after my graduation, I joined IBM Research Almaden Research Center in California, San Jose. I spent 4 years over there, and I was part of AI platform team where my role was to develop systems that can facilitate machine learning, or on which the systems that you can use to do machine learning. So this was system for ML that I used to do. So over there, I got introduced to federated learning. It's a relatively new term. So today I will be going over on how to tackle resource and data heterogeneity in federated learning. So currently, as told earlier, I joined University of Minnesota last year, in fall semester. So I'm fairly new to academia, and I'm part of the Department of Computer Science and Engineering. Let's start with what I do my research on. So my primary training has been on distributed system. There are three angles that I have been exploring from distributed system perspective: machine learning, cloud computing, and high performance computing. Today, I will mostly go over the machine learning part, how distributed systems are designed to enable machine learning. In machine learning, I will be focusing on distributed ML, node, a single node machine learning. So distributed ML is where the data that you need to train on is large enough that you need more than one node to train on. And federated learning is a subtype of distributed ML. In cloud computing, I've been exploring containers, serverless, and storage in parallel. In HPC, my focus has been only on storage sites, specifically object and key value store, and file system for MapReduce like HDFS. But I did that in earlier phase of my PhD, so it's been a while since I looked into MapReduce. So if we go forward, I have several papers in all of these areas in some venues. For ML, I have AAAI, HPDC, supercomputing, and maybe one paper which is just recently published. We got a news a few weeks back to ICSC that may have been more suitable for today's discussion, but it was not published at the time I agreed for this meeting presentation. Maybe sometime later I can present that work. In cloud computing, I have some papers in fast, Usenix, ATC, and similarly for HPC, I have been submitting to SC and HPDC. So I can start by explaining the process that goes behind my research. So my research revolves around distributed systems, and we all know that distributed systems are the building blocks for modern data application. The data size has been increasing very rapidly. We saw big data, and now we have seen boom in machine learning and AI. So all these new applications that are coming, modern application that we are seeing, they require distributed system to actually perform the computation. And with this new application, underlying distributed system face new challenges as well. It's not possible to take a distributed system that was developed a decade ago and try to use it to solve a problem, a new problem from a new application. So there need to be some tweaking, in some cases redesign or redesigning of the fundamental is required as well. So that's where my research is. What I do is I analyze the workload characteristics of modern application. For example, today we will talk about federated learning, and maybe if there's time, I can go over containers as well. So these modern applications, what are their requirements, and how can we change the existing or legacy distributed systems to facilitate these applications by better understanding these applications and changing the design or redesigning the distributed system. That this is essentially the goal of my research is.
When you speak about distributed system, are you speaking about cloud computing, on-prem computing, a hybrid mixture of those, or
Yes.
all of the above?
So all of the above. So it doesn't have to be cloud computing. So I take cloud computing as just a single part of distributed system in the initial triangle that I showed. So cloud computing is just one part. For example, federated learning has to happen on the data source, so there's no cloud over there. And similarly, high performance computing is mostly on-prem. So I include everything in distributed system. It doesn't have to be just cloud.
Thank you.
No problem. What I have been doing is understanding the workload characteristic of these application, because this opens up new opportunity to make informed design decisions that can improve not just the application performance, but also the efficiency of the underlying distributed system. So we can extract more from a given set of resources if we understand the workload characteristics better. So it's not just going to improve the application performance, but also improve the performance of the underlying distributed system. So this has been the overarching goal of my research. So today I will start with federated learning. This is a special type of distributed machine learning. So what happens in a typical distributed machine learning is that all the data that we need to train on is collected at a central location. And then we very carefully distribute that collected data on the available resources to do training of the machine learning model. But in federated learning, it's opposite. We cannot take the data from the sources to a central location due to various reasons. So I will talk about those reasons in detail after a couple of slides. What we do is that we train on the data where it is located, and we take the trained model instead, and then we combine the models taken from different sources or different parties or clients, that what we call them, and then we generate one global model. So the goal is to collaboratively build a machine learning model no matter where the data lives, by combining the outputs of different parties or clients. So there are multiple parties or clients involved. They train a machine learning model individually on a limited resources. That client could be your cell phone or a smartwatch or a sensor with not much compute capabilities, but we take whatever they can train on, and we try to combine to generate a one model that can fulfill the requirements for all the clients. So there could be many reasons behind doing federated learning, but the primary reason is always the privacy, that you do this without sharing the training data, because it's important. So there are regulations like GDPR in Europe, HIPAA, which prohibits us to actually take the data from the source and take it somewhere, for example, not even to cloud. It cannot leave the premises. There's a new California Consumer Privacy Act coming. So that these regulation make it impossible for us to train using a typical typical machine learning pipeline, that all data goes to a central data lake and then you take it from there and train. That's not possible due to these regulation. Another reason is liability. Companies are being sued because of the data breaches, so they are becoming more careful. So federated learning, actually Google came up with this term because they wanted to train on the cell phones of the users or keyboards of the user to predict what the sentence it has to be written, like what the user is typing, without actually looking into what they are typing. So they trained models on different user cell phones, and then try to combine the model to come up with a model that can work with a diverse set of users. So this is one of the liability is also one of the big issue. Another issue is that data is stored across clouds or countries, and then it's not feasible to actually move the data from one cloud to another because of the data movement cost, which sometimes become very expensive. And lastly, I think this has become another major reason is the trade secrets. Big companies like IBM or Google or Microsoft, Amazon, they don't want to collaborate with each other, thinking that they may leak some competitive edge if they collaborate or share their training data with each other, but they still want to benefit from the insights that one of them developed so that they can generate a better machine learning model. For example, if these companies are training to charge customers, to train a model how to efficiently charge customers for the cloud usage, they can do it by training individually and then sharing the models, and then combining those models to come up with a model that will work better in all these scenarios that one client or company may have seen but not others. I can give you an example in terms of a very simple data set. Let's assume it's a handwritten digits data set, and one company has digits from 0 to 8, but they have never seen a 9, whereas another company has 1 to 9, but not 0. So if they train model individually on their data set, their models will never be able to identify 0 in one case or 9 in another case, but if they do federated learning, the final model should be able to identify all the digits from 0 to 9. So there are sometimes some corner cases that one company may miss, but by combining forces without sacrificing the privacy or without sharing the direct user data, they can still achieve these goals. That's why federated learning is getting really popular these days. These four reasons, I assume, I think these are the main reason why federated learning is so famous all of a sudden. So federated learning is being used in almost like all the industries: automotive, health, finance, to fight financial crimes. It's in industries like manufacturing, where sensor data needs to be like trained on. So it's getting popular day by day, and there are many types of federated learning now even coming on. But we can talk about this after the talk if someone is interested. So I can, next I will go over what federated learning actually is. So you see over here, I have the party 1, party 2, and party n on the bottom. So these parties basically are the enterprises or clients or devices like cell phone. It could be anything. And each of them has a data set D1, D2, Dn, which they want to keep confidential. So in a typical centralized federated learning, there is an aggregator or a central server that facilitates this federated learning. So what happened is that aggregator sends a query to each party to actually go ahead and start training on their local data set. So each party or each client take this query and start doing training on their local data set and generates a reply R1, R2, and R. And this R is basically the trained model. So once they are done with this training, they send these R's replies back to the aggregator, and aggregator runs a special function which is called fusion. There are many fusion algorithm, but a simple fusion algorithm is to just average all these replies to generate a single reply. So this reply then becomes the global model. So this global model is then sent back to all these clients, and this process as a query, and this process is repeated for hundreds or thousands of times until we reach the desired accuracy or desired number of rounds that we specify. So this is the overall flow of centralized synchronized federated learning, which is the most common form of federated learning. An important point over here is that raw data from each party is never shared. It remains where it is stored. So the D1, D2, Dn never leaves their corresponding data sources. All that leaves is the trained model, and then that model is combined together using a fusion algorithm to generate a single global model that is going to be used by everyone. So this is how the federated learning essentially works. It's a very simple approach, but it's yet very effective, and it's actually getting very popular in many domains. So any question up till the federated learning, because next I will go over in detail for some of the challenges that exist in federated learning.
Well, maybe this is one of the challenges, but how do you actually go through and do explainability, with the federated learning if you can't actually see the training data?
That's actually a very good question. And this is one of the open problem. And there has been some work done on this, but there are still papers coming on. So one of the paper that I was talking about in ICSE on explainability, it's actually talks about that. So how can you ensure explainability in federated learning is that each of these steps that are being performed, if you keep track of that and you keep track of all the data that is being generated in and out, you can actually do some level of explainability, but it's not as simple as it is in typical machine learning. So there are way more challenges to be solved to enable explainability in federated learning. There is a fact sheet-based approach. This is one of my recent paper where we come up with certain questions that we want to be explained. We predefine those questions, and then we log all the data in Hyperledger to keep it immutable so that nobody can change it. And then we try to answer those questions during or after the training. So it's an open challenge right now, I would say, how to debug and enable explainability in federated learning. So here is the brief summary of what we discussed. Aggregator sends model spec and initial weights to parties train for some local epochs and then share their model weights. Once all the parties have replied back to aggregator uses fusion algorithm to combine these model and send new weights back, and this process is repeated until desired accuracy is achieved. So this is just a recap of what I just explained.
Quick question. Are there constraints on the local data, like in terms of what the individual data that you're training on at each node? Are there constraints that say like how this data should be related?
Yes, this is also a very good question. So usually it depends on the type of federated learning you are performing. See, most common type is horizontal federated learning, where we assume that each client has a similar type, or each party has a similar type of data. For example, each of them have just the words that user is writing on their cell phone. So these would be words. In some cases, this might not be the case. For example, if a bank is collaborating with a online store like Amazon to predict if a user would buy a certain product or not, in that case, a bank will have the financial history to tell if the user has enough finances to buy a certain product, whereas the online store will have the spending habit of like what has this user has bought in past. So in this cases, the data sets are very different. So the features are different. So if the features are different, then it's called vertical federated learning. So in vertical federated learning, the challenges are different. So it's a bit different problem than horizontal. But most common right now is horizontal federated learning, where all clients have already agreed upon what would be the data fields and the features are same. For example, the handwritten digits that we talk about. So all have decided that it's going to be a picture or a figure with these characteristic features. But but still there could be differences like we discussed earlier. Some clients may not have certain classes, but that still comes into horizontal federated learning because this is just the known IID-ness of the data. So what does known IID data means? That some clients may not have certain labels or classes, but the features are same. But if it's a split in features, and it's vertical federated learning with different characteristics. It's a good question, actually. I was going to go into detail later, but it's good that it came up earlier. Yeah. So I can start with one of the challenges that I have been solving in federated learning, that is how to handle heterogeneity. So there are two very visible or like very straightforward sources of heterogeneity in federated learning. One is resource heterogeneity, which means that the clients that are involved in federated learning, they may have different types of computational power, network connectivity, battery or energy sources. So they may not be able to use or do the similar type of computation on their local data. So this is resource heterogeneity, and another is the data heterogeneity. So data heterogeneity itself can be divided into two categories. One is quantity. So quantity is when the actual data is more on one device compared to another. For example, if we are training a model for some text prediction, one user may be more active compared to another user, so it may have more data compared to another. And then the second type of data heterogeneity is quality. So one of the clients or the data party may have more like better nicely labeled data, whereas other may have not as much data. For example, if we are training to identify certain dog breeds, one client may have more types of like classes, whereas the other may not have as many. So this is just an example. So data falls into quantity, quality, and resource heterogeneity. These are the most common types of heterogeneity that we see in federated learning. So in this work, we did a quick study to establish that these types of heterogeneity actually affect the federated learning process. So the metrics that we studied are total training time, the time that it's taking us to train the model, and the accuracy of the trained model. So over here on the x-axis, we have resource heterogeneity, and different patterns show data quantity heterogeneity. So what we see is that as the data size or data quantity is increasing, it takes more time to train a model. Similarly, if the resources are less, it also takes more time to train a model. But this is like a no-brainer. We expected this. Over here, we have data quality heterogeneity. So on the x-axis, we have total number of rounds, and y-axis shows the accuracy. What we see is that if the data is IID, which means that all the participating clients have same number, all the classes or labels, then it's the trained model is better. But if we restrict or limit the number of classes each client have, for example, 2, 5, or 10, what happens is that the accuracy of the trained model goes down. So we this established that data quality, quantity, and resources all are going to impact the heterogeneity. So we came up with a very straightforward solution. What we wanted to achieve was to train a model in less amount of time, but still have high quality. So what we did was we came up with an idea to split all the clients or data parties into different tiers. And we arrange these tiers based on their response time. If a client is responding fast, we put it in a very fast tier, and ultimately very slow tiers. So what it does is that it tries to limit or bound the clients which have similar response time. Typically in federated learning, what happens is that you randomly select a client. So if you end up selecting, the chances or probability of selecting a slow client with a fast client is very high. But you end up always waiting for the slowest client to reply back before you fuse the model together. So your overall time is very high. So one solution we thought about how to make the whole training faster is to just create TS based on the response time. We started with this baseline. We did some experiments on a couple of data sets. CFAR10 is image data set for different types of classes to identify what's in the image, and FEMness in extended data set, just like the handwritten digits that we talked about. And what we created several policies to generate these tiers, and we select, each policy has different tier selection probability. So vanilla is default, where we do not have any tier and we just randomly select clients. Slow is that we always selecting from the slowest tier. Uniform is that we have uniform probability of selection from each tier. Random is that we prefer a faster tier, but we still select from the slower tier as well. And fast is that we always select from the very fast tier. So we wanted to use these policies to understand the effect on the federated learning if we use these policies. So over here, we change different knobs, like the 3 knobs that we have seen so far: resource heterogeneity, data quality heterogeneity, and data quality heterogeneity. So we have 3 knobs. Over here, we are just playing with the resource heterogeneity, and data is homogeneous, both in terms of quantity and quality. So as we expected, fast is able to train really, really fast. And because data is almost like same, the difference between the accuracy is not very huge as well. We can actually, fast can also achieve good accuracy. But if we change the data quantity heterogeneity, what we see is that fast is able to still speed up, but the accuracy goes down. This is the reason, because it's not always going to be the case that fast device have high quantity of data. The most likely the client or party that is replying fast has less quantity of data. So that's why if we train repeatedly on that, our accuracy is not going to be huge. But the most interesting results we see, which is normally the case, is the data quality heterogeneity, where the data is also not same. The quality of data is also not same. So what we see is that non-IID-ness leads to lower accuracy. And if we prioritize fast here, it will make the accuracy even worse. So this shows that although we are able to reduce the training time, but we are actually sacrificing in terms of the quality of model that we are training. So takeaway is that model performance and training time, they both are interchangeable. Prioritizing some tiers over the other will definitely cause biasness, and no single static selection policy achieves faster training with an efficient model. So what needs to be done is that to find a way to achieve faster training with higher accuracy. So this is the goal of this paper. So we came up with this adaptive tier selection approach where we assign equal selection probabilities to all the tiers when we start. And then we assign credits to each tier. And we assign credits based on the response time of the tier. If a tier is fast, we may assign it more credits or less credits based on our selection criteria. And then once our tier is selected, we deduct 1 credit from it. And to offset the accuracy going down, what we do is that we ask, after we come up with a global model, we share that global model with each tier and ask that tier to find out how the model is performing on their local testing data set. And once they do this local testing on their data set, they report back their test accuracy to aggregator, central server, and central server update or adjust the tier selection probability for each of these tiers. This way, we are able to actually tackle the accuracy going down, and then we again use the random selection of our tier based on the new probabilities and deduct the credit again. So what we do with this approach is we try to balance accuracy and training time. On the one side, we are prioritizing low accuracy tiers to increase their participation and reduce biasness. On the other hand, we assign less credits to slower tiers to reduce the number of times they are selected and reduce total training time. But important point over here is that by creating tiers, we have already bounded those slower clients into a same class, so they are not going to affect the training time for the fast tier. So this will essentially automatically give us a good training time anyways. So with this balancing act between these two, we are able, here are the results. We are able to outperform vanilla and uniform selection. Over here, we have results from non-IID2, which shows that, which means that each client has two classes, 5 and 10. And we see that our system, which we call TIFL, tiered federated learning, is outperforming both the vanilla and uniform selection, and it's able to improve the model performance. So this is the accuracy part, so which was important. And here's are the results for the training time, because that's where we started from. So we are able to reduce training time by 3 to 2 times compared to vanilla and TIFL. On the x-axis, class means that it's the quality-based IIDness. Amount means it's the data quantity, and combine is that resource quality and quantity, everything is combined. So we see that we can actually achieve 3 to 2 times performance, like reduction in training time, while achieving almost same or little bit more accuracy in all these cases. So the graph on the right side, bar plot on the right side shows accuracy, and on the left side we have the training time. So this is one of the work that I have done on federated learning. So any question up till this point for the federated learning?
Yeah, so is the reason you're able to do the training on things like a PC and a phone and stuff because you've basically spread the model out among multiple laptops or multiple systems, so the model is smaller? I mean, the thing that we found at work is that we got to the point where we couldn't even do the training on our laptops anymore. We had to actually go through and do a server because the model was too big.
That's true. So in federated learning, we deliberately design a model which is not very huge, which has less number of parameters. So what we are doing is actually, and also that model is going to train on a subset of data, not all the data. And we don't know what type of resources will be available for each client. So we actually design a model which is not very huge in terms of number of parameters and layers. So these are simple models. These are not huge or complex model that we typically see in distributed ML. In distributed ML, or the server case that you are saying, what you need to do is then to move your training data set to the server as well, which cannot be done over here. So we design models which are not very big.
Does the number of participants in each tier affect? You can couch for this with various weightings, I would expect, but
Yes.
I would assume, slow the slow clients or the slow machines that you have, there would be lots of those. Fast ones would be very few or very few. Does that difference in the number of participants at each tier affect how you set this stuff up,
Yes,
or affect the results turn out?
yeah, that's true. So that's why I didn't go into detail in the fusion algorithm, but there are ways to offset that. If a slower tier is selected not many times, we can train on the slower tier with few number of time, but give more weightage when we are doing the fusion to that tier when we combine the model. So there are complex fusion algorithms available as well to offset that. And that's true. If most of the clients are slower, then unfortunately we have to select the slower tier more. It will automatically be selected more. And then the gain that we will get may not be as high. But over here we had the distribution, like the distribution between slower and faster clients with multiple distribution we actually tested with. So we still can achieve reduced training times by a factor of 2 at least. Does this answer your question?
Yes, that's kind of what that was my intuitive guess as to what it would be, but thank you for confirming.
No problem. Okay. So how much time do I have more? Just to clarify.
You have we have a hard stop at 8, so you have an hour to go, and you can open up for questions. You are the commander of the room and of the Zoom meeting.
Okay, thanks. So I think I have, in that case, I have time to go over the second project that I wanted to discuss today, which was also looking at the characteristics of the application and designing a system which can make the application run faster and better. So this is the second project which is related to containers. So we all know that containers are becoming more and more popular. We can find container for any application. You can find these containers on public Docker repositories like Docker Hub or anywhere. And more companies, they are moving towards the containers. Here's a chart for application containers in terms of total market revenue. So we see that this figure is keep increasing. I just copied this chart from one of the sources just to show the trend. So this trend is expected to keep increasing as we move forward in time, because cloud companies are moving towards cloud, and cloud is containers are facilitating this process. So before this paper or this project that we did, the container use pattern was not very well studied. So when I say container usage pattern, I mean is that, but by the way, Docker is the de facto standard for data center container management. Most of the containers, they are Docker containers. So what usage pattern means that how Docker containers are used and managed, how can we streamline the container image creation and the workflow, how these container images are used, how can we facilitate Docker performance analysis. There was no tool to actually do this performance analysis. So this paper or this project tried to answer all of these questions. So what we did in this project was we did a large scale characterization study for a real world Docker workload from geo-distributed IBM container service. So this was actually looking into the production level containers that are being run in IBM by the IBM cloud. So the idea was to provide insights and develop heuristics to increase Docker performance and develop an open source workload analysis tool. So this paper also came up with a trace replayer with anonymized traces that we collected over a period of 2 months or so from the production setup. So let's go through a little bit of background on what container images are, how container images are used, like what goes in a container image. So Docker container images can be divided into two components. One is layers. These are the actual data that is in the container image, and metadata file, which is called manifest file. So this manifest file is a JSON file which keep track of what is inside this container image in terms of what layers that needs to be part of this image and how these layers are stacked on top of each other. So user create repositories to store these images. And for example, over here, we have two users. One is creating Redis and other is creating CentOS repository images. And then image in a repository can have different tags. It could be latest version 2.6 or whatever. So latest is the default tag. If you don't specify a tag, then it automatically is assume that it's latest. And then these, if someone needs to access a certain container image from a container image store, which I will go in next slide, what it is called is, you need to have three things: user, repository, and tag. User will specify who created this image, and repository is the name of the image, and tag is the version that we want to fetch. So all these images, they are kept in an online store, which is called Docker registry. Docker Hub is the most popular Docker registry. So whenever a user does a Docker push or pull to store these images on an online store, so developer will create a Docker image using Docker create and then push it to a online registry like Docker Hub, or it could be a private registry. If it's a company like big company like IBM or Amazon, they run their own registry servers as well, because they have private clients who do not want to actually have their images go public. So in that case, they want to have private registry for their private clouds. So Docker push will send this image, container image, to the cloud or the Docker registry, and Docker pull will fetch this image back. So when this Docker push and pull commands are issued at the back end, the client on the user side, both the developer and the person who is actually fetching the image, they issue a series of HTTP requests. So for push image, we issue a head layer request. Head layer request is issued to find out if the layers that are part of this container image already exist in the container repository or Docker Hub or not. If it's not available over there, then post or put layer request is issued. And eventually, when all the layers are pushed or post or put, we issue a put manifest to update the manifest file for that container. So each layer is identified by its hash. So each layer is content addressable. You looked at the hash and find out if this hash value is in the containers in the repository already or not. If not, you put that. So even if a single bit changes in a layer, we have to upload a new layer. For the pull image, the sequence is in reverse order. First, we fetch the manifest file, and then we look into the manifest file to find out which layers we do not have locally, and then we issue get layers to get the layers that are not locally available. So this is the overall flow of how container images are stored online, and how they are, what the Docker client, local Docker client does at the back end when someone issues a Docker push or pull. Any question about Docker container images or this workflow? Okay, that's good. So there was a paper before our work that established that significant amount of time when you start a container is spent in pulling the image. And why container startup time is important, because container startup time is essentially going to tell us how much time it will take to launch an application. If you launch a cloud-based application that is running on container, you want to reduce the startup time. And if the container image is not already locally available, most of the time is spent in actually pulling the image. So we also find similar similar trend in this paper, and we then decided how can we reduce the startup time, and that's what this project is all about. So we started with collecting data from IBM Cloud Docker Registry. We studied these traces by capturing a diverse set of customers, including individuals, small and medium businesses, government institutions, and we cover 5 different geographical locations and 7 availability zones. We collected data for 75 days, which spanned over 38 million requests and 181 terabyte of data transfer between the registry and to the client. So we did in-depth analysis by first collecting these traces and studying these traces. So these 5 geographical locations that make up 7 availability zone, out of these 5, 4 are the production level: Dallas, London, Frankfurt, Sydney. 1 is staging, which was used internally by the IBM folks to actually use it internally to pull and fetch push and pull the images. And then 2 were used by the development team, pre-staging and development. Here is how what IBM Cloud Registry architecture look like. All the incoming requests go to front-end proxy Nginx, which forward these requests to Docker Registry. Registry is a online store like Docker Hub. It's an open source available Docker repository, or Docker Hub. Docker Registry is open source. So and it's a single server. So you launch multiple of these, and then control all these instances through front-end proxy. So we try to trace everything from these component: registry, Nginx, broadcaster, and then there was another component, stat counter, in IBM setup, which was used to bill the customer. So we also traced that stat counter. An interesting point over here is that we saw that container image consists of 2 components: layers and the manifest file. So layers are kept in the backend object store, and manifest file is kept in a metadata server like Redis or something. So everything, the layers goes to the back object store and then fetch from there. So we tracked all these components. So our tracing methodology was simple. We studied get, put, head, patch, and post request because these are the most common requests, and we combine traces from all these components by matching the HTTP request identifier, and we remove the redundant field and anonymize the traces. So after we collected the traces, there were certain questions that we wanted to know. The first question was to find out what is the distribution of request type. So what we find out that 80 to 95% of the requests are actually the read request or pull request. This shows that requests are heavily read intensive. And within read, most of the requests are get request, 60% of them, and 10 to 22 are head request. This established that it's a read intensive workload. Adding a cache is going to be helpful. And before this project, it was common practice to cache the manifest file, not the layers. So naturally, a question came to our mind: is it possible to actually cache the layers as well? So we looked at the typical layer size, and we found that 65% of the layers are less than 1 MB, and 80% are less than 10 MB. This shows that actually it makes sense to cache some popular layer, at least some popular layer as well. There is a significant opportunity for caching the layers. So once it was established that layers should be cached, our next question was to find out, are there certain layers that are very popular? Is there any special locality? So we saw that 1% of the most accessed layer account for 42% and 59% of the all requests in the production availability zone, except London. And we did some digging, and we find out that London is actually supporting a different version of the registry, which is not yet updated. That's why it's showing a different trend. But overall, the trend is that it's the highest or the most popular layers. They can definitely be cached, and it will definitely improve the overall performance. And here is the popularity rank for the top 10 most popular layers in each availability zone. So they can go up to 20% of the requests as shown over here. So this shows that popularity rate drops rapidly as we move from most popular to the 10th most popular layer. So up till this time, everything is very simple. And it's a simple analysis. The next question is the actually where the fun part starts. Is it possible to predict the future request before we see it? So as you saw, we in our first phase of the project, we studied what are the HTTP requests, how they look like, and we know when a user is about to fetch an image, it first fetches a manifest file, looks into the manifest file, and finds if it needs to fetch a layer or not, and then fetch a layer. So what we did in our first step was to see if how many percentage of the requests subsequent get manifest request have a subsequent get layer request. But we find out that 80% of them on average do not have a subsequent get layer request. So this was kind of disheartening for us. But we did some more digging, and we realized that in some of the cases, when the layers are already available to the client, or it's not likely to fetch the same layer again. So we need a missing piece or another piece to make a whole story. So then we came up with an idea. if someone is updating the manifest file, it means that it updated a certain layer in that manifest. So if we combine put layer with a get manifest request, then the likelihood of getting a subsequent get layer request has to be higher. And that's what we find out over here. So we see that we can have a subsequent number of get layer request if we combine put layer with get manifest request. This can enable us to actually predict when a user is going to fetch a layer from the backend object store, and we can do a pre-fetching to populate our cache. So there's a strong correlation between request, get layer request can be predicted, and there's an opportunity for layer prefetching. So we took all this knowledge and did our first set of experiments to see either caching is going to be effective or not. So over here, we did a very simple experiment. We ran a registry or a Docker Hub kind of a setup on a 32 core machine with 64 GB RAM and 512 GB SSD. For the backend object store, we use Swift object store, and we use the trace replayer that we developed from the traces that we collected. It can just replay all those traces. And what we see over here on the x-axis is the layer size, y-axis shows the latency or time that it takes to fetch that layer from that storage technology. So for the Swift is the blue, and memory plus Swift is when we are saving or storing the layers less than 1 megabyte in memory and rest on Swift. Yellow triangle shows that the layer is stored on the local file system of the registry, and it's not going to the backend object store. And the green triangle redirection, slowest one is the one where we go to the registry tell the client, here is the URL to the object store, go directly to the object store and fetch it. So we see that memory actually is going to reduce the latency by an order of magnitude. If we use faster storage technology for fetching layer, it's going to be effective. And interestingly, even SSD or local file system is also fast. So this was very encouraging for us. After this, we find out that fast backend storage or cache for the registry can significantly improve the overall performance. So we came up with an idea to design a two-level cache with first main memory and SSD based cache, where small layers of less than 100 megabyte are stored in main memory and replacement in main memory and the rest in the SSD. So now we go back to an important point that we discussed earlier. So each layer is content addressable. That's their identifier. Even if a single bit changes in a layer, its object ID also changes. So we don't have to worry about cache invalidation. This was one of a very big point for us, which made our cache design very, very simple yet effective, because we did not have to worry about cache invalidation, as each layer is content addressable and object ID is its hash. So what we did we designed this two-level cache. We assigned different cache sizes, 2, 4, 6, 8, 10% of the total ingress data that was seen by each of those availability zone. And we designed SSD 10 times, 50 times, and 20 times of the RAM cache. So it was a very simple two-level cache, memory, and SSD. Here are the results. So what we see on the y-axis is the data ingress, 2%, 4%, 6, 8, 10. These are the main memory, or the actual LRU memory that we have. We use LRU as a caching policy for eviction. And what we see is that we are able to achieve 40 to 60% of hit ratio by just using the RAM-based memory. But if we include the SSD or the second level, we are able to achieve 100% hit ratio if our main memory is designed to be 6% of the total ingress data seen by that availability zone. So this shows that it's actually possible to design a cache which can significantly or reduce the container startup time by order of magnitude if you have this caching policy. And then we also studied our prefetching, how the prefetching is performing, because our prefetching is it depends on two steps: first put layer and then get manifest, and then subsequent get layer. So there are two thresholds. T1 threshold is the time spent between put layer and get manifest, and T2 threshold is time spent between a user fetch the manifest and then fetch a subsequent get layer. So x-axis shows T1 threshold, and the different patterns show T2 threshold. So what we see is that by increasing T1 threshold, we do not see much difference in hits per prefetching, but by increasing the T2 threshold, we see a significant improvement. So this shows that it's better to have more time between get manifest and subsequent get layer request compared to the T1 threshold. So with these two policies, caching and prefetching policies, we were able to achieve very good results for the Docker registry. And then we did a subsequent work on deduplication to make sure because even if a single bit changes in a layer, the layer is stored again as a new layer in the Docker registry. So there is a opportunity to do deduplication. So we did another paper which is published in ATC 21, which talks about how to do deduplication on this data set to use less storage to store more data. So with this, any question about containers or why container startup time is important, how we did that, anything?
So was there anything you looked at other than least recently used for kicking out things from the cache? We recently had done a performance experiment with the database stuff where it turned out that the person that's setting up didn't quite have a large enough cache. And what was happening, it was doing a sequential search, and it was doing the sequential search multiple times through the same data. And it turned out that the page that it kicked out was the one, that it would be using, about 3 times after that. So,
yeah, that's a very good question. So usually when you design a cache, the policy that you use is very important, because just like the use case, the corner case that you mentioned, it can evict a data which may be needed for again. But in our case, luckily, we are able to actually predict which data is most likely to be accessed in the near future. So we were using an additional prefetching policy. So we didn't play a lot with the caching eviction policy. We just used least recently used with prefetching. But this is something that can be actually studied very quickly, because we open sourced our trace replayer, and that trace replayer has a module for different caching eviction policies. You can add a new one and do some experiment. I think there is a student who was looking into it, but he graduated recently and joined some industry or government institute. So that work is left unpublished. But caching policies do play a very important role, especially if the cache invalidation is an issue as well, where there are updates to the stored data that can also cause a problem. Any other question related to this? Okay, so I can now briefly go over on some of the work that I am doing. Hopefully I will be done soon for the question and answer. So currently I am working on accelerating federated learning by redesigning the system architecture. So I showed you guys that by just sharing the models and not the training data, we are able to ensure some level of privacy, but there are most recent attacks that have shown that a malicious client, once it gets the global model from the central aggregator, it can actually do extensive attacking to find out certain characteristics of data set used by some other clients. For example, membership inference attack. So this diagram or this figure shows membership inference attack, where a malicious party is trying to find out if a certain individual was part of the training data set or not. So there are now attacks available that enable, even in federated learning, to actually to invade privacy. But luckily there are also privacy techniques available that make this process privacy preserving. So these privacy techniques involve differential privacy, secure multi-party computation, homomorphic encryption, functional encryption, or hybrid approaches. So what happens is that once you have trained model, you apply these privacy techniques on that trained model, and then you share that trained model. You don't share your trained model as it is, but you add some privacy technique to it and then share it. The data still stays with the client and is never shared. It's just that the trained model or model update or model weights are privacy preserved through these techniques, to make sure that the malicious client is not able to extract any information from the global model. But it comes with its own disadvantages, and that's what I have been studying recently, how to overcome the overhead of these privacy techniques. They incur huge overhead in terms of communication and computational requirement. They reduce the communication overhead, especially in vertical federated learning, and design serverless computing based asynchronous federated learning is also one of the areas that I am exploring. So with this, I am open to any open questions that you have, not just related to the talk today, but anything other than talk as well.
So you're talking about privacy type things.
Yes.
And I think those 5 things that you had were applying at your central server within there. So
Yes.
how is it that if you had the trained model at D1 and D2 and DN, that those trained models had gotten passed to that server to be aggregated, how are they allowing you to actually pass that model like D1 across, if it would be possible for somebody to break privacy?
That's a very good question. So actually there are 2 locations where these techniques can be added. One is that the client or party who's doing the training, they add this privacy before they share with the central server. This is the case when the network channel and the central aggregator both cannot be trusted. But if these 2 can be trusted, then the users can share the model as it is and let the aggregator actually add privacy technique on top of the global model that it's going to share back to the client. So both approaches are being used because there are scenarios where users do not trust the central aggregator and where they can trust the central aggregator. So these techniques can be used at both location, at the client as well as at the central aggregator. Does it answer your question?
Yes, it does. Thank you very much.
No problem. Okay. Any other question, not just related to talk, even my research in general? some questions related to anything other you want to discuss. Okay. So in that case, I would like to thank everyone. Thank you so much for being so patient and giving me the opportunity to actually discuss my research with all of you. I really enjoyed your questions. They were to the point and very helpful.
Thank you very much.
Yeah, thank you. Yeah, this was fun.
Thanks, Ali.
You're welcome. You're welcome. Thanks for inviting.
Thank you very much for the presentation, and thank you, Anthony, for setting things up.